Imagine an energy source that works 24 hours a day, 365 days a year, with no sun, no wind, and no fuel required. France just made this science fiction reality. Welcome back to Curiosity AI, where we explore the scientific breakthroughs that are reshaping our world. Today, I'm bringing you a story that could fundamentally change how we think about renewable energy. While Germany struggles with wind intermittency and the UK battles cloudy solar days, France has quietly deployed something extraordinary: osmotic power. This revolutionary technology generates electricity continuously by simply mixing fresh water and salt water. It sounds almost too simple to be real, but it's not just real. It's already operational. The World Economic Forum has named osmotic power one of the top 10 emerging technologies of 2025. France's Switch Energy has launched the world's first operational osmotic power facility, and the implications are staggering. Scientists estimate this technology could supply 1/5 of the world's total energy needs. We're not talking about some distant future possibility. This is happening right now, and it could reshape the global energy landscape more dramatically than any renewable technology we've seen before. The best part? It works exactly when solar panels don't and wind turbines can't, all the time. Let me explain how osmotic power works, because once you understand it, you'll realize why this could be the holy grail of renewable energy. The science is surprisingly elegant. When fresh water meets salt water, nature creates an incredible opportunity. The salt concentration difference creates what scientists call osmotic pressure. Think of it like nature's own hydraulic system, constantly pushing water molecules in predictable directions. The technology uses something called pressure-retarded osmosis. Fresh water flows through a special semi-permeable membrane into pressurized salt water. The osmotic pressure difference creates a powerful flow that drives turbines to generate electricity. It's like having a permanent river flowing through your power plant, except this river never stops and never changes speed. The key breakthrough lies in the membranes themselves. These aren't ordinary filters. Advanced nanofluidic membranes with charged pore surfaces can convert 26% of the theoretical energy potential into electricity. Recent laboratory tests with graphene oxide membranes have achieved power densities of over 10 watts per square meter, while advanced vermiculite membranes have reached an astounding 65 watts per square meter. Here's what makes this revolutionary. Every other renewable energy source depends on weather. Solar needs sunshine, wind needs moving air, but osmotic power needs only what Earth provides in abundance: the meeting of fresh water and salt water. This happens naturally at every river delta, every coastline where rivers meet the sea, and anywhere you can bring these two types of water together. The breakthrough moment came when Switch Energy launched Opus One, the world's first operational osmotic power facility, in late 2024. Located in the Rhône River Delta near Port Saint-Louis-du-Rhône, this 50-kilowatt demonstrator proved that osmotic power wasn't just theoretically possible, it was commercially viable. Opus One uses Switch Energy's proprietary technology that combines biomaterials with advanced nanofluidics and electrode systems. The facility has been running continuously, generating electricity every minute of every day, regardless of weather conditions. This isn't a prototype sitting in a laboratory. It's a real power plant feeding electricity into France's grid. The success of Opus One has triggered something unprecedented: the Osmo-Rhône 1 project. This massive undertaking plans to deploy up to 500 megawatts of osmotic power capacity across multiple sites along the Rhône River by the early 2030s. To put this in perspective, 500 megawatts can power approximately 1.5 million households continuously. But here's the most remarkable part of this breakthrough: the economics work. Initial costs are estimated at 150 to 180 euros per megawatt hour. But Switch Energy expects these to fall to 50 to 80 euros per megawatt hour as production scales. This would make osmotic power competitive with offshore wind, which currently costs 40 to 60 euros per megawatt hour. The World Economic Forum recognized Switch Energy as a 2025 technology pioneer, cementing France's position as the leader in what could become the next massive renewable energy sector. This breakthrough is reshaping European energy dynamics in ways that extend far beyond technology. France's leadership in osmotic power represents a potential geopolitical game-changer that could shift the balance of energy independence within Europe. While other European nations struggle with energy dependence on volatile fossil fuel markets, France is building true energy independence from abundant natural resources. The Rhône River system alone could provide massive energy capacity, and France's extensive coastal areas offer numerous additional locations for osmotic power development. This geographic advantage, combined with technological leadership, positions France as a potential energy exporter in the post-fossil fuel era. Countries like Germany, despite their industrial might, have limited osmotic power potential compared to nations with extensive coastlines and river deltas. This could fundamentally shift energy influence within Europe. The global market implications are staggering. The osmotic energy market was valued at approximately $1.2 billion in 2024. Industry analysts project explosive growth to $5.7 billion by 2033, representing a compound annual growth rate of 15 to 18%. Denmark has achieved the first true commercial osmotic power operation through Saltwater's facility, which has been generating electricity since 2021 using high salinity brine from a geothermal plant. Meanwhile, the Netherlands continues research through the Osmotic project, and Norway, despite discontinuing its program in 2013, provided valuable early research that informs current developments. The race is intensifying globally. Countries like the United States, with extensive coastal areas and river systems, are taking notice. China, known for rapid adoption of new energy technologies, could quickly become a major player. The technology transfer and international cooperation dynamics will play crucial roles in determining which nations become the osmotic power superpowers of tomorrow. Let's talk about what osmotic power means for the real world and why it could solve problems that have plagued renewable energy for decades. The most immediate advantage is continuous baseload power generation. Solar panels produce no electricity at night. Wind turbines stop when air is still. But osmotic power plants generate electricity 24 hours a day, 365 days a year. This eliminates the massive costs associated with energy storage systems that other renewables require. For coastal communities and river delta regions, osmotic power offers the possibility of true energy independence. Any location where freshwater meets saltwater becomes a potential power generation site. This could transform the economics of remote communities that currently depend on expensive fuel shipments or unreliable grid connections. The environmental advantages are equally compelling. Osmotic power produces no emissions during operation and requires no fuel input beyond freshwater and saltwater. The technology operates silently, avoiding noise pollution, and has a relatively small physical footprint compared to other renewable installations. Industrial applications could be revolutionary. Large-scale desalination plants produce high salinity brine as waste. Osmotic power systems can use this brine to generate electricity, turning waste into valuable energy production. This creates synergistic systems where water treatment and power generation complement each other. The technology also offers unique advantages for island nations and coastal cities facing rising energy costs. Instead of importing fossil fuels or building expensive transmission infrastructure, these locations can generate power from resources that surround them naturally. The path to widespread osmotic power deployment follows a clear but ambitious trajectory that could reshape global energy production within the next decade. Current demonstration projects like Opus One are providing crucial operational experience and performance data. The next critical phase involves scaling to commercial-sized facilities in the 10 to 100 megawatt range. By 2030, Industry experts predict deployment of gigawatt-scale osmotic power capacity worldwide. The technology roadmap focuses on several key breakthroughs. Membrane durability and fouling resistance require ongoing improvement to reduce operational costs. Development of higher power density membranes will reduce the physical footprint of osmotic power plants, making them viable in more locations. Research into bio-based and recyclable membrane materials addresses sustainability concerns while potentially reducing costs. Advanced membranes using materials like graphene oxide and biomimetic designs inspired by natural osmotic processes show tremendous promise for approaching theoretical efficiency limits. Energy system integration represents another critical development area. Unlike intermittent renewables, osmotic power can provide baseload electricity, potentially replacing conventional power plants directly. This characteristic simplifies grid integration and reduces system costs compared to renewables that require extensive storage and backup systems. The economic outlook is increasingly favorable. Carbon pricing mechanisms that reflect the true cost of fossil fuel emissions will improve osmotic power's competitive position. Growing concerns about energy security will drive investment in domestic renewable resources that don't depend on weather or imports. France's success with osmotic power marks the beginning of what could be the most important renewable energy revolution since the development of photovoltaic cells. This technology offers something no other renewable source can provide: truly continuous, weather-independent electricity generation from abundant natural resources. The implications extend far beyond energy production. Countries with suitable geographic conditions have the opportunity to transform from energy importers to energy exporters. The technology's environmental advantages align perfectly with global sustainability goals while offering genuine energy security. What makes this story particularly compelling is the timeline. Unlike fusion power or other advanced energy technologies that remain decades away, osmotic power is operational today. The Opus 1 facility is generating electricity right now, proving that this revolutionary technology has moved from laboratory curiosity to commercial reality. The next decade will determine whether osmotic power fulfills its enormous potential. France's early leadership provides a template for other nations, but the race is just beginning. Countries and companies that move quickly to develop osmotic power capabilities could dominate what analysts predict will become a multi-billion-dollar market. For the broader energy transition, osmotic power represents a missing piece of the renewable puzzle. While solar and wind provide crucial capacity during favorable conditions, osmotic power could provide the reliable baseload generation that enables a completely renewable grid. Thanks for joining me on Curiosity AI today. If this exploration of France's osmotic power revolution fascinated you, subscribe for more deep dives into the technologies that are quietly revolutionizing our world. Next week, we'll explore another breakthrough that's challenging everything we thought we knew about what's possible. Until then, keep questioning, keep exploring, and remember that the solutions to our biggest challenges often come from the most unexpected places, like the simple meeting of freshwater and saltwater, creating the energy abundance of tomorrow.